I'm sharing my screen. Yeah. So today we discuss about decoders. Okay, what are these decoders? Okay, think my screen is visible now. Just yes. Okay. Yes. Okay. So here you see decoders. One second. Okay. So we'll see the decoders. Okay. Decoders. Decoders have n inputs, and maximum 2 power n outputs. Okay, 2 power n outputs. Okay, at a time one of these output will be active high. Okay, one of these output will be active high. Okay, will be active high. Okay, active high. So here so when the decoder is enabled. Okay, when decoder is enabled. Okay, so here if you see the block diagram for the decoder, this is the block diagram for the decoder. You have n inputs. Okay, these are the n inputs, and 2 power n outputs. Okay, 2 power n outputs, 2 power n outputs. Okay, and next so we can call this as n is to 2 power n decoder. Okay, n is to 2 power n decoder, and one more enable pin will be there. This is active low decoder. Okay, so this is active low decoder. Okay, this is the block diagram for the decoder. Okay, so we'll discuss different types of decoders. Okay, so that means how we can design like demux as decoder. So this is one of the questions. Suppose demux we already seen, no? So demux consists of how many inputs? One input, okay, and 2 power n outputs will be there, okay, and n selection lines are there, okay, n selection lines are there. So just you remove this, and these selection lines, if you are using as inputs, okay, then it becomes a decoder. Okay, so like this we can design demux by using decoder. Okay, and first we'll see about this active high enabled 2 to 4 decoder. Okay, what is this active high enabled 2 to 4 decoder? Okay, so active high enable 2 to 4 decoder. Okay, 2 to 4 decoder. So active high enable 2 to 4 decoder means you have how many inputs? You have two inputs. These are A1, A0, okay, and four outputs. Okay, four outputs. These are let us take Y3, Y2, Y1, and Y0. Okay, these are the four outputs. Okay, so one of these output will be 1 for each combination of input. Okay, so one of these output, okay, these output will be 1. Output will be 1 for each combination. Okay, for each combination. So that means encoder we already seen encoder. So that means in the inputs, so any one of the input will be 1, no? So we are getting the output by decimal means binary representation of input, no? So here the reverse. Okay, so here I will draw the truth table for this active high enable decoder. So enable pin, and here you have inputs, and you have outputs. Okay, so let us take so what are the, so this is enable pin, so what is enable pin? Let us take E. Okay, and next inputs A1, A0. Okay, A1, A0 inputs, and outputs Y3, Y2, Y1, and Y0. Okay, these are the outputs. Okay, so here if enable equal to 0, whatever may be this input, okay, whatever may be this A1 and A0, the output becomes what? Zeros only, okay, output becomes zeros only. So when enable equal to 1, our decoder will activate, okay. So if you see the block diagram, so this is the block diagram. You have A1 and next A0, A1, and this is 2:4 decoder active high enable. So this enable is active high. So when enable equal to 1, it will be activated. So 4 outputs will be given. So let us take y3, y2, y1 and y0. Okay. So if it is 0 0, if it is 0 0, so which one becomes 1? At a time any one of the output will be 1. Okay, y0 becomes 1 and enable pin is 1. If it is 0 1, so here y1 will be 1 and the remaining all are zeros. If it is 1 0, which one will be 1? Y2 will be 1, remaining all are zeros. Okay. If it is 1 1, what will be the one? Y3 will be 1 and remaining all are zeros. Okay. So like this you will get the truth table. Okay. So from this I can say that means here what is y0, y1, y2, y3. So this is y0. Okay. So y0 I can write as what? Enable A1 bar, A0 bar. Okay. And y2, y1 enable, and here if you see A1 bar, A0. Okay. y2 equal to enable A1, A0 bar, and y3, so y3 equal to enable A1, A0. Okay, A1, A0. Okay. So from this you can draw the logic circuit. Okay, for the this 2 to 4 decoder with active high enable. Okay. So how to draw this? So just here I'm drawing this. Okay. So let us take this one is enable pin, and this is what A1. Okay, A1, A0. No, A1 is given through the inverter, and this is A0. It is given through the inverter. Okay, and so what is y3? Y3 equal to E A1 A0. No, so y3. So this is E A1 and A0 connected with an AND gate. Okay, so this is y3. So y3 equal to you got enable E A1 A0. Okay, and next y2 enable so A1 A0 bar. Okay, A1 directly you take, A0 bar you take through the inverter. Okay, so this is y2 equal to enable A1 A0 bar. Okay, and y1, so y1 is enable A1 bar A0. Okay, 0 1. No, so A1 bar and A0, A1 bar A0 connected with an AND gate. This is y3. y1 equal to enable A1 bar A0, and so next is enable A1 A0. Okay, A1 bar A0 bar. So this is A1 bar A0 bar connected with a AND gate. So this is y0 equal to enable A1 bar A0 bar. Okay, so this is active high enable 2 to 4 decoder. Okay, is it fine? Do you understood your response, so that I will move forward? Okay, screen not visible. Okay, is it visible? Screen visible now? My screen is visible. Okay, sure. So see here, next I want to design. So next we'll see. Okay, next enable high and active low output decoder. Okay, so next is enable high active low decoder, enable high and active low output decoder. Okay, output decoder, enable high active output decoder. Okay, output decoder. So here so how to design? So that means here when enable equal to 1, enable equal to 1, decoder will be active, okay, decoder is active. Okay, and next so for the output, one of the output will be 0. Okay, output will be 0 for a given input combination, for each combination. Okay, for each combination one of the output will be 0. Okay, that's why active load output decoder. Okay, so I'm so how the block diagram will look like. So this is 2 to 4 decoder, 2 to 4 decoder. So here you have the inputs A1 and A0. Okay, and next enable. Okay, this is active high, and here this is active low. Okay, so y3, y2, y1 and y0. Okay, so here so I need to design this. So enable. Okay, enable, and next a1, a0. Okay, and output y3, y2. So this is input and this is output. Okay, y1 and y0. Okay, so when enable equal to 0, whatever may be the inputs, okay, you are getting the all outputs should be 1. Okay, when enable equal to 1, okay, 0 0. Okay, so y0 is what? 0, and y1 is what? So all are 1 only. Okay, at a time any one of the output will be 1. So when enable equal to 1 0 1, you are getting y1 is 0 and the remaining all are 1s. Okay, when enable is 1 1 0. Okay, so y2 is 0 and remaining all are 1s. Okay, when enable is 1 and this is 1 1, y3 is 0 and remaining all are 1s. Okay, so I want to get the expression for this one. Okay, how to get the expression? Y not equal to I'll get the max terms. No, so max terms means we already seen the POS. Okay, product of sums, SPOS, standard product of sums. So here 0 is true form and 1 is complemented form. Okay, so here if you see, so this one for 0 if you write y not equal to what? Y not equal to e bar or a1 bar, a1 or a0. Okay, this is max term. So this I can write if I apply De Morgan's law, this is e a1 a1 bar, a0 bar, whole bar. Okay, I can write like this. Okay, similarly here y not equal to e bar plus a1 plus a0 bar. Okay, so if you apply De Morgan's law, you will get e a1 bar, a0 whole bar. Okay, and this is y1, and y2 equal to e bar plus a1 bar plus a0. Okay, this you can write as what? e a1 a0 bar whole bar. Okay, and y3 equal to e bar plus a1 bar plus a0 bar. Okay, this is equal to e a1 a0 whole bar. Okay, so from this I can design this enable high active low decoder. Okay, how to design? Here I am using which gates? NAND gates. Okay, so NAND gates I am using. Okay, so see here, so how to designing? One second. Yes, so I am designing this. Okay, so here you see, so see here, so enable pin is coming. okay, enable pin. And next this is let us take this is A1, and with an inverter A1 bar, and A0, this is A0 with an inverter, okay, with an inverter. So here what is first I will write y3 equal to what? E A1 A0 whole bar, no? So y3, so E A1 A1 A0, okay, A1 A0 connected with an NAND gate. This is y3, okay. Y3 equal to E A1 A0, let us take whole dash, okay. Dash also we can represent, okay. And next is y2. What is y2? E A1 A0 dash whole dash, okay. So okay, so we already seen this, okay. So if you see y3 equal to E A1 A0 whole bar, okay. And y2 E A1 A0 bar whole bar, okay. So that I am doing. So A1 A0 bar, okay. A1, this is A1 and A0 bar, okay, connected with an AND gate. This is y2 equal to E A1 A0 bar whole bar, okay. And next y1 E A1 bar A0 whole bar, okay. E A1 bar A0 whole bar, okay. This is y1. E A1 A1 bar A0 whole bar, okay. And next E A1 bar A0 bar, okay. This is A1 bar and A0 bar connected with an AND gate, okay. And this is y0 equal to E A1 bar A0 bar whole bar, okay. A1 bar A0 bar whole bar, okay. So like this you can design enable high active low output decoder, okay. And next is what? Next is enable low active low output decoder, okay. Enable low active low output decoder, okay. So how to design? We'll see this, okay. So enable, first is what? Active low. So active high enable 2 to 4 decoder. Active low enable means what? Active low enable means here you will get E bar will get, okay. E bar, that means active low enable, okay. So when E equal to 0, that will be activated, okay. So that is active low enable 2 to 4 decoder. So here if you see active low enable so this is enable high, okay. Active high enable 2 to 4. Active low enable means so it will be like this, I think you can do, okay. So like active low enable means so here if you see active low enable 2 to 4 decoder, so the how it will look. So when enable equal to 0 only, the decoder will be activated, okay. So decoder will be inactive. When enable equal to 0 only, decoder will be active, okay. Decoder will be active, and decoder will be active. And here so at a time any one of the output will be 1. So if you see the truth table, so enable A1 A0 and what are the outputs? Y3 Y2 Y1 and Y0, okay. So here when enable equal to 1, whatever may be the A1 and A0, all the outputs will be what? 0 only, okay. When enable equal to 0 only, it will be activated, okay. So 0 1 means 0 0 means what? Y0 will be 1, and 0 1 means y1 will be 1, and 1 0 means y2 will be 1, and 1 1 means y3 will be 1. Okay, like this, okay. So how the block diagram will look like? So here this is inputs. These are the inputs A1 A0, and this is bubble you are giving through the bubble, okay. So enable you are giving through the bubble, and here you are getting the output. So y3 y2 y1 and y0. These are the outputs. Okay, 2 to 4 decoder. 2 to 4 decoder. Okay, so here what you will get, so if I want to write the expression, what is y0? Y0 equal to, just the only change is what, e bar will come. Okay, e bar, a1 bar, a0 bar. Okay, and y1 equal to 0 1, e bar, a1 bar, a0. Okay, and y2 equal to e bar 1 0, a1, a0 bar, and y3 equal to e bar, a1, a0, a1 a0. Okay, like this you will get. Okay, so this is about the active low decoder. So last decoder is what? Last decoder is enable low active low decoder. Okay, enable low active low decoder means here. So last decoder is enable low active low decoder. Enable low. The diagram you can draw. Okay, enable low active low decoder. Active low decoder. So enable low active low decoder means what here? So when enable equal to 0, then only the decoder will be active. Decoder will be active. Okay, decoder will be active. Okay, next at a time any one of the output, output will be what? Will be 0 for given combination. Okay, for given combination any one of the output will be active low. Okay, so for given combination. Okay, for each combination or for a given combination. So like if you draw the diagram, so this is let us take a1 and a0. Okay, and active low decoder. This is you are giving through the bubble. Okay, you are giving through the bubble. So if I see the block diagram, so this is 2 to 4 decoder. So if you see the truth table, enable. Okay, enable, 1 second. Yeah, so enable, and next a1, a0, and what are the outputs? Y3, y2, y1, and y0. Okay, so here if you see when enable equal to 1, whatever may be the a1 and a0, the output will be what? Here output will be active low. So active low, so that means output will be what? 1. Output will be 1. When enable equal to 0, so a1 a0 are 0 0, so y0 will be 0, remaining all are 1. Okay, and enable equal to 0, a1 a0 are 0 1. Here so here y1 will be 0, remaining all are 1. Okay, enable equal to 0 and 1 0. Okay, y2 will be 0, remaining all are 1. Okay, when enable equal to 0, a1 1 1. Okay, 1 1 means what? Y3 becomes 0, remaining all are 1. Okay, so if you means if you write the logic expression, this is y0 equal to what? Enable plus a1 plus a0. You will get the max terms. Okay, so if you apply the De Morgan's law, what you will get? Enable bar, a1 bar, a0 bar, whole bar. Okay, and similarly y1 equal to what? Enable anyway, enable will be there, and next plus a1 plus a0 bar. Okay, so just apply De Morgan's law. Enable bar, a1 bar, a0 whole bar. Okay, and similarly y2 equal to 1 0, enable plus a1 a1 bar plus a0 bar. Okay, a0. Okay, this is a0. So this is a0. So here if you see, enable bar, a1 a0 bar, whole bar. Okay, and next y3 equal to enable plus a1 bar plus a0 bar. Okay, so this is equal to enable enable bar A1 A0 whole bar. Okay, so from this you can draw the logic diagram by using this NAND gates. Okay, enable is given through the inverter. Okay, hope you can draw no logic diagram. Shall I move forward? Okay, okay, done. Okay, next you see. So this is enable active low decoder. Suppose if you want to see the 3 to 8 decoder. Okay, 3 to 8 decoder means how many inputs and how many outputs will be there. So here if you see the 3 to 8 decoder, okay, 3 to 8 decoder. So 3 to 8 decoder have 3 inputs and 8 outputs. Okay, 8 outputs. Okay, so one of the output will be 1 for each combination of the input. Okay, at a time one of the output will be 1. Okay, output will be 1 for each combination. Okay, for each combination. Okay, so here if you see, so that means this is a block diagram. Okay, so this is a 3 to 8 decoder, 3 to 8 decoder, and here you have 3 inputs. Let us take x, y, z. Okay, this is 2 square, 2 power 1 and 2 power 0. Okay, so here 8 outputs will be there. 8 outputs, 0, 1, 2, 3, 4, 5, 6, 7. Okay, 5, 6, 7. So inputs, what are the inputs? X, Y, Z. Okay, outputs are D0, D1, D2, D3, D4, D5, D6 and D7. Okay, at a time any one of the output will be what? 1. Okay, depending on this combination. Okay, so 3 inputs are there. How many possible combinations? 8 possible combinations. Okay, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, so if it is 0 means what? D0 will be 1, remaining all are 0 only, and here D1 will be 1 and D2 will be 1, D3 will be 1 and D4 will be 1, D5 will be 1. Okay, D6 will be 1 and D7 will be 1. Okay, like this you will get, remaining all are 0 only. Okay, so that is 3 to 8 decoder. Okay, and you need to implement this so you need to implement higher order decoder by using lower order decoder. Okay, how to implement this higher order decoder by using lower order decoder? So we'll see these steps. So I want to implement implementation of higher order decoder. Okay, implementation of higher order decoder. Higher order decoder. So implementation of higher order decoder, if you see, suppose if I want to implement 3 to 8 decoder, 3 to 8 decoder using 2 to 4 decoder, 2 to 4 decoder. So how to implement here you see. So like I will divide like so first I'll use first I can use the 2 to 4 decoders. Okay, so I can use 2 to 4 decoders. Okay, okay, yes. So 2 to 4 decoders. Okay, like this I can design. Okay, so 2 to 4 decoders. This is one more 2 to 4 decoder. Okay, decoder, and here A2, so A2 I am giving into the enable pin. Okay, so here I am giving through the inverter. Here also I am giving through this enable pin. Okay, and whatever the A1 A0 are there, directly I am giving. Okay, so here this is A1 and this is A0. Okay, A1 and A0. Okay, this is A1 and this is A0. Okay, A0, and this is common for these two decoders. A1 and A0 is common for these two decoders. A1, okay, this is A1, and next this one is A0, okay, A1 and A0. And how many outputs? So here for this you have 4 outputs. For this you have 4 outputs, okay. Y7, Y6, Y5, Y4, and this is Y3, Y2, Y1 and Y0, okay. So see this truth table, we already seen 3 to 8 decoder, no? So 3 to 8 decoder, so here I can consider this is nothing but let us take this is nothing but A2, A1 and A0, no? So that means here when A2 is 0, okay, when A2 is 0, which signals you are getting? You are getting the signals from D0 to D0 to D0 to D3 you are getting, okay. You are getting the signals from D0 to D3, okay. And next, so these signals you are getting, and when A2 equal to 1, okay, you are getting the signals from D7 to D4, okay. So same like that I am implementing here, okay. So here if you see, so here if you see this one, so first I will make A1 as what, A2 as 0, okay, A2 as 0. So A2 as 0 means what, enable pin, this becomes 0 and this becomes what, 1, okay, this becomes 1. So when A2 is 0, so this decoder will be active and this decoder will be deactive, okay. Active high enable signal. So we are getting the signal from Y0 to Y3, same as D0 to D3, no, okay, like that. Suppose if A2 is 1, okay, A2 is 1 means what, this becomes 1 and this becomes what, 0, okay, this becomes 1. So that means this decoder will be active and this decoder will be deactive. So in this, when A2 equal to 1, you are getting the signals from where to where, Y4 to Y7, okay. So like this you need to analyze the implement the higher order decoder by using low order decoder, okay. So like this, okay. Is it fine now? Do you understood? Any doubt in this? Your response? So that I will move forward. Okay. Okay. Next you see. Okay. Next. Next you see. Okay. 1 second. Yeah. So next, I want to implement this 4 to 16 decoder, okay, 4 to 16 decoder using 3 to 8 decoder, same method, okay, same process, okay. How to design? So you need to design 2 3 to 8 decoders, okay, 2 3 to 8 decoders, okay. Okay, so this is a 3 to 8 decoder, this is also one 3 to 8 decoder, okay. And how many inputs? Suppose like 3 inputs common for these two decoders, okay. Let us take A, B, C, and A is given like this, okay, B also given like this, and C also given like this, okay. And whatever the AB, let us take this D input is there, okay. D input is are giving through an inverter and it is giving to enable pin, okay, enable pin, and here this you are giving through the enable pin, okay. So 8 means what, here you have the inputs, okay, 4 and 8, okay, these are Y0 to Y7, okay. Similarly 1 2 3 4 5 6 7 8, okay. So these are the inputs from Y8 to Y15, okay. So that means from here you can analyze, when D equal to 0 it becomes what, 1, okay, it becomes 0. So which will be active? This will be active and this will be deactive. So you are getting Y0 to Y7 outputs, okay. And when D equal to 1, what happens? D equal to 1, so this becomes 0 and giving through the inverter. This becomes what? 1. Okay, this becomes 1 means what? Which will be active? This will be deactive and this will be active, and you are getting the inputs. Okay, these are, you are getting these inputs when d equal to what? 0. Okay, when d equal to 0, you are getting these inputs. Okay, when d equal to 1, okay, you are getting these inputs. Okay, you are getting these inputs. Okay, like this you will get the inputs. Okay, and similarly, suppose if you want to design full adder by using 3 to 8 decoder. Okay, how to design? So in the proms also, just to remember this, so in proms also we are using these decoders only. We'll getting the product terms. Okay, so there fixed AND array and programmable OR array will be there. Okay, so there also we are using, okay, this decoder. Okay, just to remember. So there also we'll discuss. Okay, how to design full adder using decoder. How to design the full adder using decoder. Okay, so you know that for the full adder, what is sum equal to a XOR b XOR c, and you got the minterms now. What are the minterms? 1 2 4 7, and next carry equal to what? Carry equal to 3 5 6 7. Okay, 3 5 6 7. So how to build this by using 3 to 8 decoder? So if you see, if you want to build this 3 to 8 decoder, so here I'm using this 3 to 8 decoder. Okay, this is 3 to 8 decoder. 3 to 8 decoder. So you have the inputs. Let us take the inputs are, you can take the inputs as what? A, B and C in are the inputs. Okay, and you have like 0 1 2 3 4 5 6 7. These are the outputs. Okay, so these are nothing but product terms. Okay, or we can call as min terms. Okay, so what are the min terms? 1 2 4 7. 4 7. This is connected with which gate? OR gate. This is connected with OR gate. And similarly, if you see for carry, okay, sum and carry. So this is for sum. Okay, and carry means what? 3. Okay, 3 5 6 7. Okay, this is 7. So this is 7 connected with an OR gate. Okay, you will get carry. Okay, you will get carry. Okay, like this you can do. Okay, so you can design a full adder, parallelly you can design the full subtractor also. Okay, by using decoder. Okay, so this is about the decoder. And one more thing, that is a priority 4 input priority multiplexer is there. So what is this? We'll see. Okay, 4 input priority multiplexer, and we can wind up. 4 input is decoder concept is fine. Any doubt in this? Just give response so that I will move forward. Anyone? Okay, it's fine now. Do you understood the decoder? Yeah, waiting for your response. Okay, next you will see. Next I want to design priority 4 input priority multiplexer. No, so I want to design 4 input priority multiplexer. Okay, once again, see here, 4 input priority multiplexer. Okay, so 4 input priority multiplexer, if you see, so this will be, so highest, whatever the highest priority signal get the least logic path. Okay, in this highest priority signal, okay, okay, get the least logic path. Okay, least logic path. Okay, and output of mux is not valid if the select signals are 0. Okay, so that we'll see. Okay, how to design this we'll see. Okay, so here I'm using 2x1 mux. Okay, and this is what this is let us take x3. okay, x3, and this is having the lowest priority, okay, lowest priority, okay, and this is d1 and d0, okay. D0 can be either 0 or 1, okay. D0 can be either 0 or 1, okay, can be either 0 or 1, okay. And next here this is s3, okay, and the output is given to this one more mux. So this is having next priority, okay, and this is d1 and d0, d1 and d0, okay, and this is selection line s2, okay, and this is given to one more dmux, 2 cross 1 dmux, 2 cross 1 mux, sorry, 2 cross 1 mux, and this is x1, okay, and this is output, and this is d1 and d0, and the selection line is s1, okay, and here this is given to one more mux, 2 cross 1 mux, so here d1 x0, and this is d0, and the output is y, okay, this is s0, okay. So this is having the highest priority, and whereas this x3 is having the lowest priority, okay. Suppose if I want to, so that means here when s not equal to 0, which one will be connected? This d naught is connected, okay. When s not equal to 1 only, this one is connected, okay. So I can write the expression. So how I can write the expression? Y equal to, so that means s naught x naught, okay, s naught x naught plus, okay, and when it will be so when s1 equal to 0, this is connected. When s1 equal to 1, x1 is connected. Next is this priority. So this priority means what? S1, okay, s1, s0 should be 0. Then why? Because this d0 should be connected, no. So then only this x1 is connected like this path, okay. So s0 bar and s1 x1, okay, plus, okay, and when s2 equal to 0, this path will be connected, and when s2 equal to 1, x2 is connected, okay. So for this, if I want to write, I want this path means s0 should be 0, s0 bar, s1 bar should be 0, s1 bar, and s2 should be 1, s2 x2, okay, plus, okay. When this one is connected, like, so when s3 equal to 0, this path will be connected, and when it is 1, this path will be connected, okay. So from this I can write s3 first I will write s0 bar, s0 bar, s1 bar, s2 bar, s3, which is connected x3. So from this we can say that this is having the highest priority, okay. x0 is having the highest priority, okay, and x3 is having the least priority, okay. So that means here highest priority, whatever the highest priority signal is there, that will get the least logic path, okay, least logic path. That's why this is called 4 input priority multiplexer, okay. So basically in the Verilog I will show you. So for 4 cross 1 mux, when you are using behavioral modeling, when you are using case statement, you will get the normal circuit diagram. Suppose when you are using if else statement, you will get this priority mux, okay. There we will see, okay. When we will discuss this multiplexer program, then you can see this, okay, when you are writing in behavioral modeling, okay. So this is about priority multiplexer.